dark matter is?
Great question. So I can answer that by saying, yes, I'll answer that. And then I can say also, I have no idea. And scientists don't have any idea. So let me explain. So our universe is made up of matter, and we know that already. And we understand how matter works because, in essence, it has gravity. There is a gravitational field. So the fact that you and I are sitting on the earth is the fact that we have mass, and we behave. You jump off a 2-story building, you will experience gravity, and it's not going to come out good. And so if we study how objects behave in our universe and we can see how they move, then we understand something about the mass of that particle, right? Or the mass of the object, because of the way that gravity works. But in the late 1990s and subsequently, there were a series of experiments, cosmological experiments, astronomical experiments for studying galaxies that looked at how they actually rotated, how they moved in a circle. And they discovered that if they measured all the mass in that galaxy, it did not, and therefore work out how much matter there was by measuring how fast it spun, remember, based on gravity, they had a problem. Because if they measured the mass by counting the number of stars and all the gases in there that they can read off, and then measure the mass about how it behaves under gravity, the mass that it had was far, far higher than what they measured. In other words, the galaxy and other galaxies as well, not just one galaxy, but other galaxies and how they work, had far more mass than what we measured. So in other words, there's some matter there, some stuff that has mass, but we can't measure it directly, but it is there. So we have no idea what it is. Dark matter. So as a result, we discover that there's a significant portion of our universe that gives it far more mass, but we can't measure it directly. Whenever we try to compare it to our direct measurements of matter by measuring the stars or measuring, and it can be done with quite great precision, and how much, but the gas that's there, they always come up less. And then there's a second problem. The other aspect is that the universe, we know, is expanding, but because the universe has mass overall, the initial view is that, well, hopefully what that does is that the gravity, because of the expansion is due to the Big Bang, and hopefully what will happen is that mass will cause gravity, cause it to come back in again. Right. And so, if you read the textbooks of the 70s and 80s, they said, well, what's the universe going to be ending like? Well, maybe we'll have what we call the big crunch. The universe will expand and then collapse in on itself and then repeat the process. Or maybe it's going to be static. So it's going to be just at the point where it just grows, and eventually the expansion is about equal to the gravity, and it'll just sit there like that. What they discovered, and which by a scientist by the name of Brian Schmidt got a Nobel Prize, he and his team, in 2011, is that the universe is not just moving out, it's speeding up. It's going faster and faster out. And so there came the idea is that, well, there's this other energy that is actually driving the universe outwards that goes against gravity, or negative energy, if you want to say it that way. And that came the term dark energy. So whenever you talk to scientists or astronomers about dark matter, inevitably they will also raise the idea of dark energy. That there is the universe, but if we measure the universe, that only 5% of our total universe is ordinary matter. Everything else is dark matter and dark energy. And so, the question then is, well, what is that matter, right? And this is the question you really ask, what is dark matter? It's the matter out there that we can't measure, but clearly it's having its influence on our universe, but we don't know what it is. So there are all weird types of names that scientists give to the possible reasons for what this dark matter is. Terms such as cue balls, which is a weird name, WIMPs, which basically means for weak interacting massive particles, but they don't know what it is, right? It's just a name. And one of CERN's desires in their experiments is that if they smash the particles, protons, hadrons, or whatever, and the other particle accelerators that occur there, is maybe they can find some evidence for particles that could explain that missing matter. But like I said, the big problem with dark matter is we can't detect it. And the way that we detect it is either it has an electrical charge, so we can bend it in electric fields and magnetic fields, or it gives off radiation, but it doesn't, none of that. And so, you know, you can fire stuff at it, you know, if you wanted to do it that way, but if it doesn't interact with it, then you'll never know. You'll never know that it exists there. You know, the fact that you are staring at my screen and seeing me is because light's hitting me and bouncing off and hitting the camera, and it's interacting with me, right? And you therefore know I'm sitting there, and I know you're sitting there. But if the light passes straight through me, then you'd never know I was there, right? So the fact is that light or particles has to somehow interact with me and cause me to do something to that in order to measure it. And right. That's the problem with dark matter. We look for all the ways of trying to do something, hit it with something, or in the case of particle accelerators, try to discover particles that could have the properties that would explain why we don't see it in our galaxies. But it's there, but we just don't know, you know, we can't directly measure it. And then that's dark matter, right? It's dark because we don't know what it is. You know, it's out of our vision, so to speak, but it's definitely showing its influence.